Welcome back to ECE 441A, 541A. A week from today is the second exam, as a reminder, and before that we have a couple of homework assignments due. One is due on Monday, and I have corrected the last problem page. Instead of design problem 5.4, I replaced it with the correct problem, which is computer problem 5.4 on homework number 4. Let me know if there's other errors in the material that you have been provided, but there should be practice material for exam number 2 available on D2L, and obviously the homework assignments and the problem statements. The following Friday after the exam we won't have class. That's engineer's breakfast, that's homecoming week, and the following Monday after that is lab number 2, and I did try to grade lab number 1, and I'm returning that, and if you're a distant student, I'll try to maybe upload that to the Dropbox as feedback, a scanned version of your graded exam or lab number 1. The main problem that I was seeing with some of the labs was, one, you were getting the weight wrong. The weight or the mass is supposed to include the carriage. A lot of people didn't include the 500 or the 0.5 kilogram contribution of the carriage, and they were also maybe getting the time to peak wrong, which if they were getting a time to peak of 6.19, they were saying, oh, I have a time to peak of 6.19, but it's really relative to when you actually kicked the system, and you kicked it again at 6, and so your time to peak is the 6.19 minus the 6. And so some people were getting a very, very tiny omega sub d because they were using that large 6.19 number for their time to peak. And it's really that time difference between when it gets kicked and when you see the peak subsequent to that. Today what I want to do, and we may circle back around and talk a little bit more about steady state error, but today I want to provide material on the Routh-Hurwitz stability criterion. Has anyone heard of that? The Routh-Hurwitz stability criterion. This will be new, and what we're going to do is build up an array that allows us to actually determine stability of a polynomial based on some algebraic tests and not having to factor that or find the roots explicitly. That's the idea behind the Routh-Hurwitz stability criterion. We'll start by trying to find values of a gain in a problem that give us stability, and then we will talk about the Hurwitz test. So we're breaking up this Routh-Hurwitz stability test into two pieces. The first is a quick Hurwitz test that basically says, are your polynomial coefficients all present and are they all positive? That's necessary, it's not sufficient. So if it violates that, you can say, oh, I don't have a stable polynomial, and if that's all you're asked, you're finished. But if you need to know something a little bit more, then we need to build up the Routh array, and we'll talk about 3 possible cases. There's 4 cases that are discussed in the book, and the 4th case is one that doesn't happen very often, and let's just concentrate on these first 3. But there is a 4th possible case. We'll try to get through some examples, and then we will return and look at another way or another example of where we might have an adjustable parameter with which we want to determine the range of that parameter for stabilizing the overall system. Let's start with that question on the first problem, and that is, can you find a value or values or a range for this adjustable parameter k to produce a stable closed-loop system? And let's now try to construct or build the system that I'm wanting to illustrate this concept with. Here, let's say we have a transfer function k over s plus 2, and that could actually be representative of a controller that you might build. You might now create this with an op-amp and some summing junctions and some gains. We now are applying that to a system. Let's say the system is governed by the transfer function 1 over s minus 1. And in terms of this system, can you tell me anything interesting about that system besides, well, what's its order? What's the system order? I'm sorry, of just the system. Of just the system, what's the system order? First order. And in combination with the controller, we have a cascade of a second order. But the first, just looking at the system itself, can you tell me anything about that first order system? It has a positive pole, doesn't it? And in that case, positive poles are not really positive in the sense of right or positive. It's actually, now that's an unstable system, isn't it, if the pole was in the right half plane. So this is actually an unstable system, and we want to stabilize that, which it won't be stabilized if we just had this cascade combination. We actually need to measure the output of that system and feed it back. And here we will have negative unity output feedback. You might hear me say that. It's unity, meaning there's no gain in the feedback path. It's negative because we are comparing it with this applied input, or the reference input, R of S. And we now want to determine, or try to answer that question. Is it possible to select a gain or some range of gains in this controller that will stabilize the closed loop system? That's the question. And if we're interested in the closed loop system, what is the first thing we probably want to do? Is find that closed loop system's transfer function. And that's now T of S. And if we combined both of these effectively and just said, oh, let's just call that G, now we can use cheer number 2, which is, whoops, I didn't want it in red. I didn't want it to scream that much. We have G over 1 plus GH. What's H? That's the gain in the feedback path. That's 1. Let's not even put it in there. So our closed loop transfer function is G over 1 plus G, where G, like I said, is this combination, cascade combination of the controller and the plant. So we get sometimes fast and loose. We play fast and loose with what we're calling G or G and G sub C, etc. But hopefully it's clear from the context. This is now K over S plus 2, S minus 1. If we plug that G in and cancel the common denominator in the numerator and the denominator, I'm going to do that all in one step. We end up with K, and then we have S plus 2, S minus 1 plus K. That's the closed loop transfer function after doing G over 1 plus G. Oh, those labs that I'm returning are ordered based on spring, I think. So spring 1 systems are at the top. It's not alphabetical by the student group. I wouldn't know how to do that. And then it goes by the number of masses. So spring 1, mass 1 will be at the top, and spring 4, mass 4 labs will be at the back of that collection of papers. Here's our closed loop transfer function, and for stability, what piece of that or what part of that are we interested in? Or are we needing to worry about the whole thing for closed loop stability? We really are concerned with the denominator. That's going to give us our poles. The denominator polynomial is what governs stability. And in this case, it's S plus 2, S minus 1 plus K. And if we multiply that out, we have S squared plus 2S minus S, which gives us S, minus 2 plus K. And that's now a second order polynomial, and we want to try to pick K, if we can, to make that polynomial stable. That's the idea. What we are going to learn in just a few minutes is actually a sort of a nice little piece of knowledge that applies only to a second order polynomial, but we play a lot with second order, so it comes in very handy. We are going to learn the following. If we have a monic second order polynomial, that is, or i.e., if we're dealing with something, if it's monic, the leading coefficient is 1, and if it's second order, then our highest power is s squared. Let's say that that's now plus a1s plus a sub 0. That's the monic second order polynomial generically that we might want to know something about. This monic second order polynomial is stable if and only if, that's the IFF, I'm assuming we're tweeting this information or texting, so we're trying to minimize characters. If and only if its two coefficients, which are a sub 1 and a sub 0, actually are there, and that's what I'm meaning by are present, and they both need to be positive. We're now saying if we have a second order monic polynomial and a1 is positive and a sub 0 is positive, we can immediately conclude that we've broken our stylus, that our polynomial is stable. And if you're listening to this, you're having no idea what I'm talking about. But hopefully I'll return to a stable. Yeah, this is a good day. So let's apply this to our example. Hopefully I can still write. Here's our example. It's s squared plus s minus 2 plus k. What is a sub 1 in this example? What's my a sub 1 coefficient? It's hiding right there, isn't it? There's a sub 1, and it's equal to 1. What's a sub 0? It's that linear combination. There is a sub 0. So now what we want to do with those two identified from our example, we now want a sub 1, which is 1. We want that to be bigger than 0 in order to be stable. And 1 is positive, so we're good there. Then we need to look at a sub 0, which we've now seen as minus 2 plus k, and we want that to be bigger than 0. And now we have an inequality that involves k, and we can solve that for k to conclude that for that system to be stable, we need to crank up the gain k to be bigger than 2. If we go back to this original system, as long as we have k bigger than 2, that closed loop system is going to be stable. Obviously, the bigger k is, the more that pole is going to be pushed into the left half plane. Right at 2 is right at the boundary of stability. And we've then been able to take an unstable system, which had a pole at plus 1, and actually bring that pole into the left half plane by using feedback and a controller and adjusting the gain k. That's what we're doing, and that's what we hope to be starting to do in this class, is developing strategies for designing, stabilizing, and other types of controllers that do more than just stabilize a system. Let's see where that rule came from concerning second-order monic polynomials and develop in general what we will call the Routh-Hurwitz stability criterion. And what we want to do is use this to try to help us determine, is our system stable or not, or are the poles in the left half plane, or the LHP. I may just start abbreviating that as LHP. And we actually want to develop a process or a technique that doesn't rely on us actually factoring that polynomial. 10th order polynomial, we don't want to find all 10 poles. We want some algebraic approach that will allow us to determine when that system or that polynomial is stable. So we want a method for determining pole locations when this polynomial is our denominator polynomial without actually factoring that polynomial, let's say d of s, where now we're thinking about a transfer function t of s being a ratio of polynomials. The numerator polynomial we might represent with capital N of s, and the denominator polynomial is capital D of s, and that's now our closed loop system. In this particular case, the Routh-Hurwitz criterion is actually based on algebraic tests on the coefficients in that polynomial, which typically is the denominator polynomial if we're talking about a system stability. But if you simply wanted to look at a generic polynomial and find out if all of its roots are in the left half plane, you can apply the Routh-Hurwitz criterion. The textbook then uses a couple of different labels for the polynomial that we might want to be examining. They may call it delta of s, they may call it q of s, so you just have to sort of know what's being used. So I'm going to use what they're defining in some of their equations. And the generic polynomial we will now label or parameterize as a sub n is the coefficient of s to the n. And then a sub n minus 1 is the coefficient of the s to the n minus 1. And we just keep going down to a sub 1s plus a sub 0. That's how we will define our polynomial in this discussion. The first piece of the Routh-Hurwitz test is the Hurwitz test, and that's the simple one. But just be clear that this is a necessary test and not sufficient unless we're dealing with a second-order polynomial. But right now, in general, the Hurwitz test is a simple test that will tell us if our system is unstable. Simple test to decide if the system or if the polynomial, if we're talking about a polynomial, has any root in the right half plane. And that Hurwitz test is as follows, as we've already sort of hinted at for the second order case. We need all of the coefficients in our polynomial to be present, meaning they need to exist. We can't have any zero coefficients. And 2, all of the coefficients are positive. And as I said before, these are necessary, but not sufficient. They're necessary for stability, but not actually sufficient. Which means if this polynomial that we are examining, if delta of s fails, and it could fail in 2 different ways. It could fail with a missing coefficient, or one of those present coefficients could be negative. That would be a failure of the Hurwitz test. If delta of s fails the Hurwitz test, then if that's all we need to determine, then we know that we have a root in the right half plane, or our system is unstable. However, if that polynomial delta of s passes, the Hurwitz test, it's just like if you pass a test, that doesn't necessarily mean you're graduating, right? Ouch. Well, you might have to do more than just one test in that case. But here, if delta of s passes the Hurwitz test, then that really doesn't give us enough information. We need more information. So if you just pass one test, we need more information. You have to pass more tests, don't you, in class? But here, if we're dealing with a polynomial, then if it passes the Hurwitz test, we need more information. And that more information is actually going to be provided by creating or building an array that we are going to call the Routh array. And here's the procedure behind that array. And let me, before we even build this Routh array, I don't want to get distracted by the construction of this object. Let's just talk about the object right now. Let's construct the Routh array in the first step. And then once we've built the Routh array, this collection of numbers that sort of looks like a matrix, but it's going to have a more of an upper left triangular shape to it, there are actually 3 possibilities that result, or 3 possibilities that we will talk about. One, the first case, is that in this array of numbers, we will be examining the leftmost column of that array of numbers, and we'll be looking at something relative to that leftmost column of numbers. All left column entries in case A let me say all left column entries in the array are non-zero. That's our first case. So we look and we have everything is there. We don't have any zeros in the left column. We have something in each of the entries of that left column. Then what we do is we count the number of sign changes that occur as we look from top to bottom in the number of rows in this Routh array, and based on that number now implies or tells us the number of roots in that polynomial with positive real parts. It doesn't tell us where they are, it just tells us how many that are in the right half plane. It tells us the number of roots with positive real parts. It doesn't tell us whether we have complex by just counting sign changes. It just tells us the number. Here's an example of what I'm trying to say relative to this left column of numbers. Suppose that the first row entry has a positive coefficient, the second one is positive, the third is negative, and the last one is positive. Let's say this is representing our left column, the signs of our left column elements. With that pattern of plus, plus, minus, plus, how many sign changes do we have? 2. So we have plus to plus, no sign change. Plus to minus, there's a sign change. Minus to plus, another sign change. That pattern, even though it has one negative, it has 2 sign changes. Is that clear? If the bottom 2 were flipped, if we went plus, 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 minus, how many sign changes would we have? 1. Is that clear? All right. So this now says that we have 2 sign changes. And if that was in fact the case, how many roots would be in the right half plane? We would have 2. All right, that's the first case. The second case, case B, is now in that left column. Let's say that we have a left column element in the array is actually 0 with non-zero elements elsewhere in that row. That is, suppose that we were looking at the s to the 5 row, and this will make more sense when we start building the array. But let's say we built this array, this Routh array, and the s5 row had a 0, then the non-zero elements elsewhere in that row might be 4, 7.2. So we're going to have a rows of numbers, and we're concentrating on what's in the leftmost column of those rows of numbers. What we do, if this is the case, if we're building our Routh array and we stumble upon this 5th row that does this, then what we do in order to continue is we actually replace that 0 with a positive number. So we now just put this and we say, oh, let that be epsilon. And then what we do is so once we have that, then we couldn't build our Routh array any further until we replace that 0 with an epsilon, and now we can keep building. Because what we're going to find is we're dividing by this left column element as we go further down in the Routh array construction. So we need something there. We give it an epsilon, and then we count the sign changes in the entire Routh array in the left column as this introduced parameter epsilon goes to 0. So we count the number of sign changes as epsilon gets tiny, and then we say, oh, we've found so many sign changes And luckily, this is consistent with the first case. However many sign changes we have is the number of roots in the right half plane. So this gives us the number of roots with positive real parts. The third case that we will consider is the case where one row might be completely zero. Every entry in that row is zero. We have an all zero row. Question? So I'm picking epsilon to be zero or positive. So now I'm letting it approach zero from the right in a sense. So now you don't have to worry about, wait a minute, my epsilon was negative and now I have some subtractions. If it's positive, it makes things cleaner. And now you just let it get small and see what happens, because you might have epsilon minus 4. And now as epsilon gets small, that coefficient is close to minus 4, so it's negative. So you would then say, oh, that's a negative. And that might then impact the number of sign changes. The third case is if the entire row is zero when you're building up this Routh array. Then we have to do something a little bit more interesting. Now we have to rely on our calculus. Now we go up to the preceding row and form an auxiliary polynomial. We'll flesh all of this out, and we differentiate that auxiliary polynomial and substitute that into the all zero row. Let me try to say that. So I now want to say if we end up with an all zero row, we replace that all zero row with the differentiated auxiliary equation. And again, we count the sign changes. After we've done that replacement with the differentiated auxiliary equation, and consistent with the previous, the number of sign changes will be the same as the number of roots with positive real part. And as I was discussing that, this auxiliary equation is created from the row immediately above the all zero row. Now that's the 30,000 foot level of the Routh array construction, and well, we haven't talked about the construction of using the constructed Routh array to tell us something about the number of roots in the right half plane. Let's now go down a little bit and try to build up this Routh array. And maybe some of you, if you do have your hard hats, you can put that on now that we're entering the construction phase. No. We were talking about dividers, now we're talking about hard hats. We're trying to touch everybody, okay? All disciplines. Yes? So now the question was, in this second case, in case B, we were talking about 1 0, but you could have some zeros in that row, but they all can't be 0. So I hope I've worded that with non-zero elements elsewhere in that row. So you could have some additional 0 elements, but you have to have some non-zero in that row. Does that answer your question? Pardon? No, no, you don't replace all of those zeros with epsilon. That was the question. Do we replace all of our zeros with epsilon? No, we just replace the left element that's 0 with epsilon, and then we continue our construction. We leave the other zeros alone. We use those as whatever they are, which are 0, to build the rest. Now, here is our Routh array construction. We start with, and now I'm calling it D of S. It's delta of S, Q of S, or D of S, but you know what it is by context. This is A sub n, S to the n, plus A sub n minus 1, S to the n minus 1, etc., plus A1S plus A sub 0. And now you may not see this in books, but I sort of like to have a way of keeping track of where I'm at in building this, and so I introduce what I call a bookkeeping column, which tells me something about the row that I'm in. You won't see this necessarily, but since this is an nth order polynomial, and little n could be 5, it could be 8, so this would be my s to the 5 row, or s to the 8th row. But once I have s to the n, then I just keep going down until I run out of s. I just go s to the 0, and then I'm finished. But in the s to the n row, I take the first coefficient, a sub n, and then I hop over the next coefficient, and I take the next one, which is now a sub n minus 2. And that pattern repeats until I run out of coefficients. I now would step over the a sub n minus 3 and put down the a sub n minus 4, a sub n minus 6, and I just keep doing that until I run out of coefficients. Is that clear? So now we're sort of playing hopscotch. We hop over coefficients after we've started with the highest one. Then in the second row, we pick up those that we hopped over. In the second row, which is the s to the n minus row, we put in the n minus 1 coefficient. Then we hop over the n minus 2, and we say, oh, now, or then we just insert the a to the n minus 3, a to the n minus 5, a to the n minus 7, etc. That we just write down by inspection of the polynomial. The rest of the Routh array is going to be constructed. So that now, if I want the, let me go ahead and put some more rows in here. Now I want a, or s to the n minus 2. I'm going to now build that up with a b1. Let me try to color code this. A b sub 2, and maybe a b sub 3. And I just keep building until I run out of columns to my right in the preceding 2 rows. Everything in this construction will be based on the preceding 2 rows above a given row. And then we have the s to the n minus 3, and let me put some c's in here, c1, c2, and I just keep going, like I said, until I get down to s to the 0. And then I have created, I build up my Routh array. Let me now tell you how to build the b's and the c's. Okay. B1. B1, these subsequent rows are created based on the 2 rows above it. For B1, and I'm always using the elements in the left column as 2 of my coefficients that I will use to build. So with B1, I use the ones right above it and 1 column to the right. And B1 is going to be, and it's really just the negative of a determinant, but I'm not going to introduce determinants. You just have a sub n minus 1 times a sub n minus 2 minus a sub n times a sub n minus 3 all over a sub n minus 1. And all of this process will continue to use that column, the left column, in creating this. So what did I just say? I now said that B1, to build that, you had A sub n minus 1 times the first row in this case, which was A sub n minus 2, minus A sub n times A sub n minus 3 all over A sub n minus 1. Is that clear where B1 came from? Now B sub 2, again, plays with AN and A sub n minus 1, the two leftmost, but now it works with one column to its right. So that now, to get B sub 2, I would take A sub n minus 1 and multiply it by A sub n minus 4, and then subtract A sub n times A sub n minus 5, and again divide by A sub n minus 1. That's B sub 2, which is in red. So let me say that B sub 2 now still plays with the leftmost column of two rows above it, A sub n minus 1 and A sub n, but now it goes one row to its right, or one column to its right, which in this case was now A sub n minus 4 minus A sub n times A sub n minus 5, again divided by A sub n minus 1. Do you get the pattern? If I need B sub 3, if I haven't run out of columns to my right, I just keep building B's. So B sub 3 is going to be what? Do you see that it's still going to be there, but now it goes one column to its right, and then A sub n with A sub n minus 7, divided by A sub n minus 1. Question? So the question is, what happens when I start running out of coefficients? What happens when the top row has more non-zero coefficients than the next row? You just put in zeros. And if you now have to multiply by that 0, you multiply by that 0. I think that was the question. What happens if you have an unequal number of entries in your two rows above the row that you're trying to build? So in this case, B sub 3, you just make them 0 and use that 0 in your products. You now have A sub n minus 1 and A sub n, but now you have A sub n minus 6 and subtract A sub n and A sub n minus 7, but still divide by A sub n minus 1. Now do you see what's going to happen with C1? To build C1, you play with the two rows above it, and you take B1 times A sub n minus 3, subtract from that A sub n minus 1 times B sub 2, and divide by B sub 1. And C sub 2, you work with the column to its right, which is B sub 3, A sub n minus 5, and also A sub n minus 1 and B1, always that column in the left. So C1 is now B1 A sub n minus 3 minus A sub n minus 1 times B2 all over B1. Then C sub 2, again you play with the left column two rows above you, so it's B1 and A sub n minus 1, but now you use the column 1 to its right, and you would now have B1 times A sub n minus 5 minus A sub n minus 1 times B3. Is that clear? B1 times A sub n minus 5 minus A sub n minus 1 times B sub 3, again all over B1. And you just keep doing that until you fill up the S to the 0 row, and that's only going to have one element in it. You don't go any further. All right, let's look at an example of that. And let's start easy. Let's start with this general second order polynomial, or in really what we're doing is we're trying to justify that the Hurwitz test is necessary and sufficient for a second order polynomial that's monic. Here our delta of S is this S squared plus A1S plus A sub 0. What's our Hurwitz test tell us? That was our necessary condition, wasn't it? And the Hurwitz test says I need to check if all coefficients are present and if they are positive. And we don't know yet what A1 and A sub 0 are. In a generic sense, they're just coefficients, so let's see what they need to be. We really need more information in order to work with this particular case. So now, let's build up the Routh array. And our Routh array now, what's our bookkeeping tell us we have in terms of in the leftmost column? What do we put in that leftmost column for our bookkeeping? S squared, that's the highest, and then we just keep decreasing that by 1. So now we have S squared, S1, and S to the 0. What's in the S squared row? Is that what I heard? If that's what I heard, it's not correct, is it? So you need to start with the first one, which was 1. It was monic. And then you jump over the next coefficient, which was A sub 1, and you pick up the next coefficient, which was A sub 0, and we're out of coefficients, we stop. So this first row isn't very long, is it, or very wide? What about the second row? Now we jump one order of S less than the highest, S to the 1, and we start with that in this case and keep going. So what's in the S1 row? A1 or A0 or 1 or both or all of the above? It's just A1, isn't it? Now we have to build the S to the 0 row. And how do we do that? Well, let's say that that's B1. In this case, what is B1 going to be? We have A1 times A sub 0 minus 1 times 0. Since this was one of the questions before, wasn't it? What do I do now? I have a 0 there. Well, I just use it as a 0. And then do I divide by something? By A1. And what's that actually end up being? Now my A1s cancel, and this is now A sub 0. And if I want, so this is now my, let's just say that I now have a completed, you won't have to do this really for you. You would just sort of say, oh, I can replace this with A0. But let me say that I now have a completed Routh array that looks as follows: S squared, S1, S0. In this case, it was 1, A0, A1, A0. And now what do I want? For stability, what do I need? Or for all of these roots, I have two roots in this quadratic, and if I want them all in the left half plane, what do I need for these left column of elements? You don't want any sign changes, do you? So 1 is positive. You need A1 to be positive, and you need A0 to be positive. So we've just shown that the Hurwitz test is necessary and sufficient for a second order. It's not for any other higher order. But using this test, we've now demonstrated that if you have a second order and you have coefficients that are present and positive, you can immediately conclude all of my roots are in the left half plane. And we'll pick up at that point with more examples on Monday.